Okay, in this video, I'm going to run through the relationship between the discrete time Fourier transform and Fourier series, but Fourier series with a little twist. So instead of doing the Fourier series in the time domain to represent things in frequency, we're going to do Fourier series in the frequency domain to represent time. Okay, so that sounds like a challenge, but it's not really that bad. Let's talk about it. All right, so first of all, let's remember what to do with Fourier series. Okay, so let's say I had something periodic. Just draw some periodic waveform. Okay, if we were going to represent this periodic signal in frequency, one of the things we do is look at the Fourier series coefficients. Okay, so if this is f of t, all right, then f of t can be written as a sum from n equal minus infinity to infinity of Cn e to the j n omega naught. Okay, I'm going to use capital omega here. Omega naught t. Okay, capital omega because we're in continuous time frequency here. All right. So we like this because the omega naughts are the harmonics. All right, and the Cn's tell us the weight of each harmonic. Okay, and then we have a formula for calculating the Cn's. Okay, that formula would be you do 1 over the period integral over any period of f of t e to the minus j n omega naught t dt. Alright, so that's Fourier series where this is time. Okay, well let's turn this around and let's say we have a periodic signal in the frequency domain. And it's no coincidence, this looks like the sum of replicas that we've talked about before once you sample a signal. Alright, but this will still work. Alright, so here's Fs and minus Fs. Okay. I'm sorry, that's not right. This is Fs. Okay, this point is Fs over 2, minus Fs over 2, and minus Fs. Okay, so this is a periodic waveform. We're going to call that x hat of f. Once again, that x hat of f is periodic. All right, and because it's periodic, it would have a Fourier series. Okay, so notice what we did in the time domain when we had a Fourier series. We would choose a fundamental frequency. Okay, so what we would need to do in this discrete time is choose a fundamental time. All right, and so our fundamental time is going to be the period, the sampling period, cap t. All right, that plays the role of omega naught. Okay, so then we noticed here that when we did the Fourier series expansion, the time variable remained the time variable. Okay, so that's still a t. All right, so when we do our Fourier series, we would still have an f variable. Okay, so bear with me. We'll keep going. All right, so this would have a Fourier series. It would be the sum from n equal minus infinity to infinity of some coefficients. I'm going to call those the alpha n's for right now. Okay, before it was the Cn's, so I just needed a different letter. So alpha n, all right, e to the minus j. All right, the 2 pi f. F is the continuous variable, so I don't, that needs to stay continuous because this is a function of f. And then I need the equivalent of omega naught. Okay, in the time domain, the equivalent would be capital T. All right, and then just like I had with Fourier series, integer values, I'm summing over the n's, this would need to be an n right here. Okay, so if I did that and I notice way back up here with the definition of the discrete time Fourier transform, this looks exactly the same. This plays the role of the alpha n's. Okay, so the alpha n's are actually the sample values. All right, so I can erase that and replace it with x of nt. All right. So the cool thing about the Fourier series is once you have this written down, you can find the x of nt's, all right? Just like we could find the Fourier series coefficients, and you've done that several times in your academic career. We could find x nt. It would just be an integral, 1 over the period. Okay, the period in this case is going to be fs. Okay, so it would be 1 over fs. Right, that's how often this thing repeats itself, every fs. Okay, integral over any period, so it might as well be minus fs over 2 to fs over 2. Okay, of the function we're taking the Fourier series of. All right, it seems weird because it's a function of f, but that would still work. E to the minus j 2 pi f t n. All right, df instead of dt. All right, so everything's working just exactly the same. It's just we're interchanging the role of time and frequency. Okay, so I don't know, I think that's pretty cool because if you think about it, this gives you a way of going backwards. All right, so if you had a certain x hat of f, you could take this backwards. This would be the inverse DTFT. I stands for inverse. And you would be able to recover the original time samples if you had the spectrum. Well, this is going to be useful for us because we're going to use that to design filters a little bit later on in the course, especially when we do FIR filter design. Okay, so what I want to do next is, what if we normalized frequency? If we normalize frequency, all right, then what happens is this becomes, the period fs becomes 2 pi, okay, because we know everything repeats every 2 pi in omega, so omega is normalized frequency in radians per second. Okay, this would be integral from minus pi to pi. Okay, this would be x hat of omega. Okay, e to the minus j omega n d omega. All right, so that's the more common version of the inverse that you'll see in textbooks, but I did want to show you that really the inverse discrete time Fourier transform essentially comes from Fourier series. All right, I think that's a really cool and elegant mathematical result, and I hope you come to appreciate it.